Hello there, Mr. Sutton bringing you this lesson on the alternating series test. In this one, we're going to be using the AST to determine convergence, and we're also going to determine absolute versus conditional convergence. For the warm-up on this one, pause the video and see if you can remember the alternating series error bound. Alright, so the way this went, if you have the terms of a series that alternate and decrease in absolute value all the way to 0, then we were able to say that the error was bounded by the absolute value of the next term. So this unique back and forth progressively smaller and smaller property of alternating series that decrease in absolute value to 0, in addition to helping us bound the value of the rest of the series basically, they also help us prove convergence. If we add and subtract by ever smaller amounts, a series is going to have to converge. Just to get a visual demonstration of this, let's say I have the series -1 to the n plus 1 over n. So basically 1 minus 1/2 plus 1/3 and so on. So let's say that you add 1, then you subtract 1/2, add 1/3, subtract 1/4. We can see this is getting closer and closer to some converging value. So this leads us into something called the alternating series test for convergence, which says if the terms of a series alternate and decrease in absolute value to 0, then the series converges. So it's basically the same conditions as alternating series error bound, just a different conclusion more relevant to what we're doing here. We're going to actually apply the alternating series test now to this example. So first thing you need to do, first off, we recognize that we've got this -1 to the n plus 1. So that's the big tip-off that we might be able to use the AST on this one. So first, we need to mentally verify the conditions of the alternating series test. You don't actually have to write all of this out. You should write it out on your guided notes just so you know what I'm mentally envisioning here. But this generally happens in your head, and then you just state the conclusion of all of it. So here's our little mental thought bubble here. We need to verify that this is alternating mentally. We have that piece with this -1 to the n plus 1. We also need to verify that we are decreasing in absolute value. So that means that the n plus 1th term, or the absolute value of it anyway, so that would be 1 over n plus 1 times n plus 2. We need to verify that that is less than the term right before it, so less than 1 over n times n plus 1. And we have to verify that that's actually true where this series is happening, so for n greater than or equal to 1. So is this actually true? Well, here we have a denominator that's going to be larger than over here. Bigger denominator means smaller fraction, so this term is always going to be less than this other term, at least if we're dealing with all these positive numbers. The last thing we have to verify is that we're actually going to 0 with that nth term, so we need to think about the limit of our nth term as n approaches infinity, and since this is bottom heavy, we can see that yes, indeed, this is going to 0. So once we've verified all this in our head, we need to actually state that each of these conditions is met, and then talk about the alternating series test. So the wording I always use is that the terms alternate and decrease in absolute value to 0. Therefore, this series converges by the alternating series test. Here are two examples for you to try out. Pause the video and see if you can show the work needed to get these done. Alright, so for the second example here, we notice that we've got some alternating going on. So this meets the alternating part of the alternating series test. And we've got terms that are decreasing in absolute value. The denominators are getting bigger without any change in the numerator, so these are definitely getting smaller. And if we go all the way to the nth term, 1 over the square root of n, the limit of that is 0. So we see that the terms alternate and decrease in absolute value to 0. All of those are actually met. Therefore, this converges by the alternating series test. And then we've got this one down here. So for this one, it would help if you rewrote this. Cosine of pi n, that's equivalent to -1 to the n. Because again, with all the multiples of pi, taking the cosine of those, you are bouncing back and forth between negative and positive 1 without hitting anything in between, because these are all the integer values of n. So this is 1 pi, 2 pi, 3 pi. We don't hit any of those in between values. All right, given this series, we see that we are clearly alternating. We are definitely decreasing as we go. The denominator just keeps getting bigger and bigger, so the whole thing gets smaller. And the nth term will indeed be 0 if we take the limit of this. So we can say that this has terms that alternate and decrease in absolute value to 0. Therefore, this series converges by the alternating series test. For our next example, we're going to roll several problems into one. So here are three different series. Which of the following of these converges by the alternating series test? Pause the video and see if you can figure this out. All right, so let's take them one at a time. Option 1 here, -5 over n. So let's go through the conditions of the alternating series test. First off, it has to alternate. Does number 1 alternate? Well, we've got this negative in here, but we have to be careful because this is not being raised to any power. So we're not actually flipping back and forth between negative and positive. We are always getting negative numbers. -5 over 1, -5 over 2, -5 over 3. We could actually think of this as being equivalent to the series -5 times the sum of 1 over n. This is essentially the same thing. So in this case, we see this 1 over n. This is actually the harmonic series. So this does not converge at all. It diverges, actually. Taking a look at the next one, this one is definitely alternating. We have the -1 to some exponent, and it's an exponent that's not going to force this to be positive. But now if we take a look at whether or not these are decreasing, it looks like they are. We've got n over n plus 1. The denominator is bigger. However, is it decreasing to 0? What is the limit of the nth term on this one? Well, the limit of n over n plus 1 is actually 1, right? Because we forget about the plus 1 here, and it's just n over n. So this is not 0. This thing actually fails the nth term test. So this is going to diverge. And you might be wondering, well, is it possible to diverge by the alternating series test? And we see at this point it isn't. If there's any divergence happening, it's because of the nth term test. The alternating series test generally only proves that things are converging, if you can meet all the conditions. Now we go to the last one here. We've got alternation. This is definitely decreasing, and the limit of all this is going to 0. In fact, this is a special series. This is the harmonic series, but alternating version of this. It's called the alternating harmonic series. And in fact, if you see this one on the AP test, you are allowed to simply identify it as the alternating harmonic and say that therefore this is going to converge. It's kind of like we know the harmonic series diverges. Well, on the AP test, we know the alternating harmonic series converges. So at the end of the day, option 3 was the only one that actually converged, so choice D. For this next example, we're going to do a slightly different kind of problem. Now we're not just concerned with convergence. We want to determine whether the series converges absolutely, converges conditionally, or diverges, and then give reasons for any of these. So what's this whole absolute versus conditional kind of thing? Let's define that. When we have absolute convergence, that means the series is converging with an absolute value wrapped around it. So this one, if we wanted to prove it converged absolutely, we would need to basically forget about this back and forth negative versus positive and just only consider the positive version of all these nth terms. Now, conditional convergence means that the series converges only without the absolute value. So typically this is going to be an alternating series that converges in this fashion. So when we're trying to test for absolute versus conditional convergence, we're going to start by testing for the absolute convergence. Because if it converges absolutely, it can't converge just conditionally. We don't care about this piece if we already know it converges absolutely. So we're going to test for absolute convergence first. We're going to consider this series with no alternation in it. So just 1 over n is what this is going to come out to. And we see that this series here is the harmonic series, so that it diverges. The conclusion for this, then, is that this series does not converge absolutely. But we're not done. It still might converge conditionally. So to see about the conditional convergence, we have to test the original series for that conditional convergence. So we look back at the original here, just the way it was. Now this we see is the alternating harmonic series. We just saw that in a problem before. We know the alternating harmonic series converges. We actually don't need to do anything more to prove it than this, just identify it. So therefore, we would say that this series converges conditionally by the alternating series test, or by the fact that it's the alternate harmonic series, either of those reasons. Here's another example asking about absolute versus conditional convergence. Pause the video and give it a shot. All right, so for this one, we'll test absolute convergence first. So the absolute value of all of this is just going to be 1 over n squared. Now, does this converge? Well, this is a p-series with a value of 2, which is greater than 1. So this does, in fact, converge absolutely by the p-series test. And since we've found that it converges absolutely, it's not eligible to converge conditionally. Conditionally, remember, means you converge only without the absolute value. So that's it. We are done with this lesson unconditionally. Until next time, Mr. Sutton signing off.